Welcome to the 24-23 video on extraction. The purpose of extraction is to separate or purify compounds by extracting a substance from a solution into a solvent in which it is more soluble. And as an example of that, I have a solution here, compounds A and B. And the solution has been placed into a separatory funnel, which is normally what we use in laboratories to separate solutions at the laboratory scale. So typically extractions are done from aqueous solutions, although that doesn't have to be the case. So we're going to assume this is an aqueous solution of two soluble compounds, soluble in water, A and B. Compound A is more soluble in an organic solvent than it is in water. Compound B is more soluble in water. It would be a salt or something like that. So we put the solution in the separatory funnel, and then we're going to add an organic solvent. And I think the solvent that I'll use here is ether. And of course it's important that the solvent that you're adding is not miscible. So this is ether. And note that I drew the ether layer on top of the aqueous layer. And the reason for that is that the density of ether is less than the density of water. So density when you're doing extractions is an important physical property of the solutions that you'll be extracting into or from. The denser solution will of course be on the bottom, and the less dense solution or solvent will be on the top. Solvent layer will be on the top. So look up the densities. Now there's one complication there, and that is that the densities of these solvents changes when you dissolve substances into these solutions. So this solution of A and B, this aqueous solution, will not exactly have a density that is the same as water because there's stuff that's dissolved into it. And once things get dissolved in the ether density will change as well. So you have to be very careful when you're doing extractions not to throw away anything, not to throw away either layer until you're absolutely certain that you've got what you want, that you've got the layer that you want. Because sometimes the less dense solvent can end up on the bottom if the density changes enough when you dissolve solutes into it. So we've got our ether layer on top. The next thing that we're going to do here is add a stopper. So we can shake this thing up. So there's our glass stopper. And normally you kind of turn this upside down and shake it. So we're going to shake this thing up and down vigorously to make sure that the solvents are thoroughly mixed. Now one problem, it's not really a problem, but it's something to be aware of. So we're vigorously shaking this back and forth, is that when you mix these solvents together, even though they're miscible, there is a little bit of, often a little bit of dissolution that occurs of one solvent layer into the other and to each other. And there's an enthalpy change associated with that dissolution, the enthalpy of solution. And often that's exothermic. And solvents like ether have relatively high vapor pressures. And so you can, when you're doing the shaking initially, there's a little bit of warmth created, and that really increases the vapor pressure inside the separatory funnel. That can cause the stopper to pop off even if you're gripping it really tightly, or leak. And in those cases, you lose some of your solution. It gets on your hand, and that's kind of a mess. So when you first start shaking, it's a good idea to turn it upside down, and pointing this away from you into the fume hood, you vent this. That is, you open up the stopper down at the bottom of the separatory funnel. And that releases some of the pressure. You do that 2 or 3 times, and then it's not a problem anymore because the temperature is equilibrated and there's no more increase in vapor pressure. So remember to vent whenever you're doing an extraction with volatile organic solvents. So after we've shaken this thoroughly for a few moments, what are we going to have now? You can probably guess that the solutes are now partitioned in between the 2 layers, or in the 2 different solvents. So the more soluble compound in the organic layer, A, is now in the ether layer, and the more soluble compound in the aqueous layer, B, is now in the water, dissolved in the water, and we've effectively separated the 2 compounds. So what remains next, of course, is why we used a separatory funnel. We open up the stopcock and drain the lower layer into one flask, so that will give us our aqueous solution of B. Then you switch flasks, open up the stopcock again, and drain the top layer into another flask, giving us our organic solution of A, which can be easily vaporized to leave pure A behind. So that's the basic idea behind liquid-liquid extractions and the use of a separatory funnel. Okay, I'd like to go into a little bit more detail in the theory now, because that has important implications for our procedure when we do extractions. And what I'd like to talk about is the partition coefficient and the concept of doing multiple extractions versus single extractions. So the partition coefficient, which is abbreviated K, it's like an equilibrium constant, is the ratio of the solubility of a compound and two immiscible solvents. So as long as the partition coefficient is greater than 1, that compound can be extracted into a new solvent from a solution that it's already in. As an example, we're going to extract, just a theoretical example here, we're going to extract 6 grams of compound A, which is dissolved in 100 milliliters of aqueous solution, into an organic solvent, and again we'll use ether, and we'll assume that the partition coefficient for this extraction is 2, which means that essentially the compound is twice as soluble in ether as it is in water, given equal volumes of both of those two solvents. Now we're going to do this extraction twice. The first time we're going to do this extraction, we're going to use a single extraction of the 100 milliliters of aqueous solution with 50 milliliters of ether. And it's really very easy to calculate how much of the compound A in this case will be extracted in the ether solution if you know the partition coefficient, which is right here, it's 2. So the partition coefficient K is equal to the solubility, and this is in grams per milliliter. So X grams of our compound A will be extracted into 50 milliliters of ether over the solubility in the aqueous solution in the denominator here. We're starting with 6 grams of the compound total in the 100 milliliters of aqueous solution. As we do the extraction, that's being reduced by X, which is being transferred or extracted into the ether layer. So that's what this equation is telling us. Solubility of A in ether over the solubility of A in grams per milliliter in the aqueous solution. It's more soluble in ether. That's why this partition coefficient is greater than 1. So we extract one time with 50 milliliters of ether, and when we solve our equation here for our one unknown, that's the grams extracted in the ether solution, we end up with 3. So what this means is that a total of 3 grams of A is extracted into the ether if we extract once with 50 milliliters. And that's really not that good, because that's only half of the compound. The remaining half remains in the aqueous solution. So we're going to try something different. We're going to use, in the second extraction, we're returning to our original solution, which has 6 grams of compound A dissolved in 100 milliliters of water. We're extracting with ether again, but this time we're using, again, a total of 50 milliliters, but we're doing it twice, once each time with 25 milliliters of ether. So we can calculate again, using the same equation, the amount of compound that will be extracted into 25 milliliters of ether from 100 milliliters of the aqueous solution. And it's less, as we would expect. Okay, the math tells us that we get about 2/3, 2 grams instead of 3 of A extracted into 25 milliliters as we do into 50 milliliters. So we get less compound extracted out. But using the same total amount of solvent now, we're going to add another. So it's very important you realize what's happening here. So we've extracted once with 25 milliliters of ether. That's in our separatory funnel. We remove the bottom layer and then isolate the 25 milliliters of ether into a separate flask. Then we're going to pour. Remember, the ether was on top. So we have to drain out the aqueous layer, then drain out the ether layer into a separate flask. Then we're going to put the remaining aqueous solution back into the separatory funnel. Okay, our 100 milliliters of solution that now has 4 grams, right here, 4 grams, let's scroll this up a little bit, of compound A in it. So we've re-added the aqueous solution to the separatory funnel. Now we add another 25 milliliter portion of the ether to that 100 milliliters and extract again. Shake it really well, vent it. The whole drill that we talked about previously. This time there's less compound A in the aqueous solution, so we get less out, only 1.33 grams when we solve this equation. Now here's the key though. We combine, so we separate the 2 layers again, we combine the 2 ether layers for a total of 50 milliliters of ether, just as what we used with the single extraction in the first case up here. Now in those 2 layers, when we combine them, we've got a total of 3.33 grams of A extracted. Now compare this, the 3.33 grams right here, to the 3 grams in the first case. This is always true. Okay, so what I'm trying to show you here is that multiple extractions with the same amount of solvent are more effective, that is, get more of the compound out of the first solution, out of the original solution, than a single extraction with a larger volume. Okay, so multiple smaller volume extractions, even when the total volume is the same, 50 milliliters in both cases. In this case, again, we extracted twice with 25 milliliters. In this case, once with 50 milliliters. So the total volume of ether was the same. But doing sequential extractions is more effective in that it gets more of the compound out of the first solution. That's really important. So kind of the gold standard in laboratories, and this is what I was used to when I did research, is as long as you've got a reasonable extraction coefficient, is that you extract about 3 times. 3 extractions, after about 3 extractions, you get diminishing returns. So 3 extractions is going to get a reasonable majority in most cases. Again, that depends on the partition coefficient, but that gets a majority in most cases of the compound out of the original solution. So that's something to bear in mind. Next thing I'd like to discuss is the purification of acidic compounds, acidic organic compounds by aqueous extraction, which is, if you're lucky enough to have an acidic compound to be working with, this is a really, really useful way of purifying compounds like carboxylic acids and particularly acidic alcohols, anything that has a relatively acidic proton. So to do this, we're going to add a base to an aqueous solution of your neutral compound, the compound that isn't significantly acidic. In this case, we'll choose some non-acidic alcohol, something like butanol or cyclohexanol or something like that, something that's going to be relatively soluble in an organic solvent. And an acidic compound, in this case, a carboxylic acid. So there's our carboxylic acid functional group. So when we add a base, we'll use sodium hydroxide. There's really just one reaction that occurs here. The sodium hydroxide is going to slightly ionize the alcohol as it does with water, but not tremendously. We could say that the equilibrium, as long as we don't add too much sodium hydroxide, lies to the right here, or to the left rather, and that is the unionized alcohol is what predominates. Carboxylic acids, being much more acidic generally than alcohols are, will be easily deprotonated, and this reaction will essentially go to completion. And so one thing I forgot to write here is that once the hydroxide deprotonates, this is the acidic proton, the carboxylic acid, which we haven't studied yet, deprotonates the carboxylic acid, you're left with, of course, a salt. We know that from general chemistry. So there's our salt. And so we got an oxide anion here and a sodium cation. That's our 2 ions in the salt. This, of course, is dissociated in the aqueous solution. And water. Now, salts, we know, are an extreme case of polarity, and so those are going to remain more soluble in aqueous solution and much, much, much less soluble in a neutral organic solvent. The unionized neutral organic compound, in this case this alcohol, is typically most neutral organic compounds, uncharged organic compounds are going to be more soluble in organic solvents. You have to choose the proper organic solvent, of course, than they are in aqueous solution. So we're going to add this basic mixture of these 2 compounds right here, the aqueous solution of the 2 compounds, into our separatory funnel. We add our organic layer. In this case, I chose ether again, so it's on top. It's less dense than the aqueous solution. You shake it up, you vent it, and when the 2 layers separate again, after they've been mixed thoroughly after a thorough shaking, you scroll this up a little bit so we can see this a little bit better. There we go. The 2 layers separate after shaking, and as I mentioned, the salt, which is very, very polar, remains in the aqueous solution. The neutral alcohol is effectively extracted in the ether. You should do this 3 times, remember, with 3 different ether layers, separating each time. All that remains is to separate the 2 solutions, and you've separated the 2 compounds. Remember, the ether and the alcohol were both originally in this aqueous phase. So we've got our salt in aqueous solution, or salt of the carboxylic acid, and the neutral alcohol in the ether solution. Now there's one more thing I should mention here. If you want the alcohol, you're done. All you have to do is evaporate the ether and you've got your alcohol. But what if you want the carboxylic acid? What if that's the compound that you actually desire? Which is often the case when you're trying to purify an acidic compound. The next step in that case would be to add an acid to the solution. So we're going to add some aqueous acid. I'll choose hydrochloric acid, HCl. So we're going to add some aqueous hydrochloric acid to that solution. Now, the carboxylic acid, this is a carboxylate anion, which is a base now. That's going to be protonated by the hydrochloric acid. So let me draw that acid-base reaction. So if we want to isolate the acidic compound, we're going to add acid, as we did right up on top there. We're adding HCl. That's going to neutralize your carboxylate anion here. So here is the reaction. So there's the carboxylate anion. We add our HCl. Remember, that's the sodium salt. I left the sodium out. It's a spectator ion. In an acid-base reaction, this anion is going to pick up that proton from the hydrochloric acid. Remember, the hydrochloric acid really exists as protons in chloride in the aqueous solution. And that neutralizes, reforms our carboxylic acid. The chloride will pair up with the sodium, and so that's our new salt. And this is again is a proton transfer Bronsted acid-base reaction. So what do we do now? Well, the next thing we do, of course, is a second extraction. So I'm going to redraw our separatory funnel. So now we've got our water, our aqueous solution with our neutral carboxylic acid and some sodium ions and chloride ions in that solution. So once again, I'm going to add an organic solvent, and I'll stick with ether. You have to carefully choose your organic solvent because sometimes carboxylic acids aren't very soluble in ether, for example, in which case you'd of course choose a different solvent. The solvent has to be immiscible. And so here's our ether. So we cap this, shake it up, vent it as we did previously. And again, it's best to do this 3 times. So cap it, shake it, vent it, drain out the bottom layer, add another layer of ether, cap it. Oh, and I forgot to mention, I think I forgot to mention this earlier. This thing, these separatory funnels will not drain unless you take the stopper out, because air needs to get in here to replace the fluid as it goes out. If you open this up without taking this out, really, you might get a drop or two out at the bottom here, but nothing really happens. So you have to take the cap out to drain it. So of course, as was the case above, this neutral compound is now more soluble in the ether layer than it is in the aqueous layer. And so it gets extracted. This goes up here into the ether layer and is extracted out into the organic solvent. And so once we do this several times, we end up with an ether solution, organic solution of our carboxylic acid, which is now purified. And our isolated carboxylic acid. And to completely isolate the carboxylic acid is very easy. You just evaporate the ether. So this is how you can take advantage of the acidic properties of certain compounds, carboxylic acids, acidic alcohols, and so forth, to purify them by extraction. As we saw with acidic compounds, we can also purify basic compounds by aqueous extraction. And the process is almost identical, only in this case we're adding an acid to the aqueous solution of the basic solute and any non-basic impurities. Generally the basic solute, most often the most common basic organic substance is an amine, and I've represented that here. An amine is a compound with trivalent nitrogen in it. And so we're going to add an acid to a solution of a neutral organic solute, the impurity, and the basic amine. And the acid that we'll add is hydrochloric acid. So here's our neutral compound. The hydrochloric acid doesn't react because it's not basic. The base, though, the amine, does react with hydrochloric acid in a Bronsted acid-base reaction, proton transfer. So this basic amino group is going to pick up the proton from the hydrochloric acid and make an ammonium ion, just like an ammonium ion, only there's carbon bonded to the nitrogen now. And if you're using hydrochloric acid, you make the hydrochloride salt. So this is a salt. We're making a salt in the acid-base reaction, just as we did in the previous example when we added a base to our carboxylic acid. And just as was the case in that example, the salt, which is charged, is an extreme case of polarity, and it's going to be much more soluble in aqueous solution than our unionized neutral organic compound, which is going to be more soluble in the neutral organic solvent. And so we're going to take the solution, as we did previously, and put that into our separatory funnel and add our organic solvent. So this was the original aqueous solution here, so water is the solvent. It had the amine, the neutral compound. Now we added acid, hydrochloric acid, then we added the ether, capped it, shook it real well, and allowed the two phases to separate. And now we've separated the two compounds. So the neutral unionized compound, being more soluble in the ether, partitions into the ether phase. And the ionized basic compound, no longer base, the protonated basic compound, the protonated amine, which is now ionized, remains in the aqueous solution. So you take the cap out, drain the aqueous layer into one flask, switch flasks, drain the organic layer into another one, and we've effectively separated the two compounds. Now often you want to isolate the basic compound, the amine, and so we do that just as we did when we wanted our carboxylic acid in the previous example, only in this case, instead of adding acid to this salt solution, we're going to add a base. And the base we'll use is sodium hydroxide. It doesn't have to be sodium hydroxide, it can be sodium carbonate. Anything that's basic enough to pull that proton off will work. And that, of course, is the next step. So to isolate the basic amine, we add base, and we get an acid-base reaction, Bronsted acid-base reaction again. So here's our ammonium salt. The sodium hydroxide, this of course gets ionized. The hydroxide ion pulls a proton away from the ammonium ion, regenerating our neutral amine, which is often referred to as a free base, and a salt. So the acid reacts with the base to produce our conjugate base and our neutral free base. So we're going to take that solution, place it back into the separatory funnel. And so this is the aqueous solution originally. We add ether to it, stopper it, shake it up, vent, as we always do. Allow it to, the phases to separate, and the neutral base now is more soluble in the ether. And it gets extracted to the ether, leaving the salt behind in the aqueous solution. You drain this out and then drain this into a separate flask, removing the ether, leaves you with your free base, the free amine. So you purified that, you've removed that from the non-basic organic compound. And so anytime you've got an amine, this is often a very effective way and a very easy way of purifying amines. So we're now ready to talk about the microscale extraction of caffeine from tea, which is of course what we're doing in the experiment in the lab. And the first thing I should mention is that caffeine is an amine base, so it's a basic compound, a basic solute. The major impurity in tea that we're separating the caffeine from are tannins, which are acidic compounds. They're acidic because they're composed of phenols. That's our major impurity. So we got to separate the two bases. We're going to separate the caffeine from the tannins based on the fact that one is an acid and one is a base. We know how to do that. And there are actually two ways we could do that. In the first way, we could take advantage of the fact that caffeine is a base, and we could react the caffeine, this being the structure of caffeine, it's an amine base, this being the most basic nitrogen in the caffeine molecule. We could add acid to the caffeine, and if we added hydrochloric acid, we'd protonate this nitrogen here, making it into a salt. That would make the hydrochloride salt of caffeine, caffeine hydrochloride, which would be more soluble in the aqueous phase. That would leave the phenols as neutral compounds. And so if we added an organic solvent, we tend to extract the phenols into the organic solvent, leaving the caffeine in the aqueous phase. Since we want the caffeine, we could separate the aqueous caffeine hydrochloride, add base to it to reform the free base, and then extract that into an organic solvent like ether or dichloromethane. We'll be using dichloromethane. So that's one possibility. The other possibility is what I've shown here, and that is instead of adding acid to this aqueous solution of these phenolic tannins, this is our tannins of phenol. Phenol is an alcohol where the OH group is on a benzene ring. That's known as a phenyl ring. We haven't really talked about those yet. That makes these alcohols much more acidic, for reasons we'll talk about later on in organic chemistry, than our normal aliphatic alcohols. So these are especially acidic alcohols on these phenols and the tannins. So phenols are a common feature, structural feature of tannins. So we're going to, instead of adding an acid, we're going to add a base to this solution. So what's the base going to do? Well, the base doesn't react with the free amine caffeine, so there's no reaction. But we know that the sodium carbonate, or base, will deprotonate the acidic phenols. So any one of these three protons could come off, probably more than one comes off. I'll just show it with one of them. So the carbonate from the sodium carbonate will pluck a proton or protons off these acidic phenols, and in doing so, will ionize them. And so the sodium from the sodium carbonate remaining in the solution will form a salt with the alkoxide of the phenol of the tannins. So we form the salts of the tannins. And as we've talked about previously, these salts are much more polar than neutral organic compounds, and so these are going to tend to stay in the aqueous phase. We'll extract this basic solution with an organic solvent, dichloromethane, to remove the caffeine, leaving the charged tannins behind in the aqueous solution. So let's talk a little bit more about the extraction itself. One more thing I should mention about adding the base. There's another couple of advantages of adding the sodium carbonate or base. The first is, because the caffeine is in tea and we have all these acidic compounds in tea, these acidic phenols, it's not unlikely that at least some of the caffeine is protonated, exists in the protonated state. And if you protonate caffeine, that's just an example, with hydrochloric acid, you get caffeine hydrochloride, which is what I've drawn the structure of here. So this, remember, was the most basic of the nitrogens in the caffeine molecule. And so this is protonated caffeine. This nitrogen is charged. If you did this with hydrochloric acid, you'd have chloride hanging around, you'd have caffeine hydrochloride. That's a salt. That's very soluble in aqueous solution. That's not going to be extracted from the aqueous solution significantly into an organic phase. So by adding the carbonate from the sodium carbonate, that would deprotonate any of the caffeine that's protonated that exists in the ionized form as a salt, regenerating the free base, which is much more soluble in the organic solvent. So that's another advantage of adding the base to the solution. It converts any protonated caffeine to the free base, which is going to be, you're essentially greatly increasing the extraction, the partition coefficient as you go from this to this. So this is much more soluble in the organic phase than this is. A second, maybe minor advantage of doing this is a concept known as salting out. We're forming a salt. We're forming salts by adding the sodium carbonate from these acid-base reactions. The sodium carbonate itself is a salt. By adding salt to the aqueous solution, you're making it more polar. You're increasing the charge of the aqueous solution. And that kind of reduces the solubility of neutral organic compounds like the caffeine-free base in the aqueous phase, which can help drive this into the organic phase when we do the extraction. So adding salt to an aqueous layer in an extraction will tend to make the organic compounds want to leave into the organic phase. And again, we're increasing the partition coefficient by the salting out process. So that's another advantage of adding salts like sodium carbonate, in addition to its basic properties, to these aqueous phases and extractions. I'll conclude with some specific comments about our microscale extraction procedure. First off, with our microscale kits, we don't have a microscale separatory funnel. So instead of a separatory funnel, we're going to be using our cold fingers, the same cold fingers we use for the sublimation experiment. So you'll be putting your tea into the cold finger, and then you'll add your dichloromethane. dichloromethane being the organic solvent that we'll be extracting the caffeine into. So we've got our tea with our sodium carbonate and our free base caffeine, our tannins are in there, our ionized tannins. We add the dichloromethane. Then we're going to cap this. So there's a little plastic cap. You may have noticed that in your kit already. That fits on top, a little round plastic cap that fits on top of the cold finger. And you're going to shake this really well. So you shake it really, really well. And I forgot to mention a few important points here. Make sure that when you're making your tea, you keep the volume of the tea below 12 milliliters. The reason being, of course, is if this is more than 12 milliliters, there's not going to be enough room in this cold finger, enough volume to accommodate both the tea and the 2 milliliters of dichloromethane that we'll be extracting with. So keep the volume of the tea below 12, maximum of 12 milliliters. So we cap the little test tube, really the cold finger, not using it as a cold finger here. Shake it really well, and remember you've got to vent. In fact, I have drawn something to show you how to do that. Here we go down below. So there you go. So here's you, you're the student. And when you vent this thing, as soon as you start to shake it, you want to vent it. Because if you don't do that, dichloromethane's got a very high vapor pressure. There's an exothermic enthalpy of mixing. When you start mixing the dichloromethane with the aqueous phase, the pressure builds up here rapidly. If you don't vent this, the cap's going to pop off and you're going to get sprayed with the solution, which is not only going to stain your clothes, but the dichloromethane is, I should mention, a carcinogen, so you want to avoid exposure to it. So we're going to be doing this in the fume hood. So when you vent this, you just pull the cap up on one side away from you. So you're going to pull it up in the direction towards the back of the fume hood, away from you, so that if anything sprays, and it probably will since this is wet up here, it sprays away from you. So don't have this pointed towards anyone and not yourself. So open it up towards the back of the fume hood, then snap the lid back on and continue shaking. And you want to do that about 2 or 3 times. Once you've done that 2 or 3 times at the beginning of the extraction, the solution is no longer getting warm and you no longer have that buildup of vapor pressure. So don't forget to vent the solution. Additionally, recall that it's more effective to extract multiple times with small volumes than it is a single time with a large volume. So we're going to extract 3 times with 3 separate 2 milliliter portions of dichloromethane. So forgot to mention, dichloromethane has a density of about 1.33 grams per milliliter at room temperature. That is greater than density of water. Remember, the tea is an aqueous solution. And so we're expecting this to be on the bottom. Now remember, the tea is going to be very concentrated, and so the density of the tea is going to be greater than the density of water. You always have to be careful when you're doing extractions not to throw any of the layers away until you're absolutely certain you've got what you want. So don't discard any of the layers until you're done with the experiment, really. So you'll add the 2 milliliters of dichloromethane, shake it, vent, shake it some more, vent, shake it a little bit more, and vent. You want to shake it vigorously. So once you've done that, you're ready to remove the bottom layer, the dichloromethane layer. And so to do that, you're going to stick one of the long stem Pasteur pipettes. That's the Pasteur pipette with a long pointed end on it. If you try to fit one of the regular Pasteur pipettes in here, this thing's going to overflow. It takes up too much volume. So get one of the long stem Pasteur pipettes. And you're going to put that all the way to the bottom and draw up the dichloromethane. Okay, it's a good idea to kind of be squeezing the bulb of the Pasteur pipette as it's going through the aqueous phase, through the tea. That prevents the tea from getting into the pipette. You'll have little bubbles coming out rather than the tea going in. And then you draw up the dichloromethane into the pipette, take that out, and put that into a separate flask. So the dichloromethane layer goes into a separate flask. It's probably better to leave a little bit of dichloromethane behind than it is to try to get all of it and contaminate the dichloromethane with the aqueous phase. So it's okay if you leave a tiny bit of dichloromethane behind, because remember, you're extracting 3 times anyway, so you're going to be adding more dichloromethane. So once you separate the dichloromethane, then you're going to add more of the dichloromethane, 2 more milliliters, cap it, and repeat the process. You do that 3 times. So you cap it, shake it up again, may have to vent it, maybe not, and remove that, add that to the original 2 milliliters, so you'll now have 4 milliliters after the second extraction. So we've just doubled this. There we go. And then you add 2 more mils for the third extraction, cap it, shake it up real well, and combine all 3 of those extractions into the same flask. So that's what I mean by 3 separate extractions. I always say this, and what I often see students do is they'll add 2 milliliters, shake it up, they'll add 2 more milliliters, shake it up, and then they'll add 2 more for a total of 6 milliliters in here if you even have enough room for that. That's not 3 separate extractions. That's 1 extraction with 6 milliliters, which is not as effective as 3 separate extractions where you separate each of those 2 milliliters and then add more. So make sure you understand that. So one thing I forgot to mention, and that is what to do if you see an emulsion. Emulsions are mixtures of immiscible liquids, 2 or more immiscible liquids, they've been thoroughly mixed, and you have little tiny droplets of one of those liquids that's thoroughly dispersed into the other liquid. And so what happens then is in an emulsion you don't get this nice separation between the 2 phases, you just get this mixture. Milk is an emulsion. Emulsions can be very, very stable. They can sit around for hours, days, weeks, maybe even years without separating. So you don't have enough time to let your emulsion sit. Now, if you run out of time during the lab and we've come to the end of the lab period, we'll continue working on this lab the next period, you can just let your mixture sit, and the emulsion might break over a period of a couple of days or over the weekend. But if you're not at the end of the lab, we want to break the emulsion. We want the 2 phases to separate so that you can separate them and do another extraction or just collect the dichloromethane layers together. So one way of breaking an emulsion when we've got a small amount like this is to centrifuge it. So if you have an emulsion, we're going to use the centrifuge. And rather than try to explain how to do that there, that's something that I'm going to have to show you how to do. So one last thing to mention, once you've separated the dichloromethane layers, water and dichloromethane are not miscible, but that doesn't mean small amounts of each won't dissolve into the 2 different layers. In other words, you may get a little bit of dichloromethane dissolving into the tea and a little bit of water and the dichloromethane. And even if you didn't, there's a good chance, it's probably likely that you're going to get some aqueous solution into the organic phase when you're separating them. And so we need to get the water out of the organic phase, away from the caffeine, so that we can isolate the caffeine. And what we're going to do, one way of doing that, now if you get little droplets of the tea in here, you can try to pull those out as much as you can with your Pasteur pipette. After you've done that, the way we're going to dry the dichloromethane is by adding a drying agent. There's several drying agents. What we're going to be using is anhydrous calcium chloride, and there'll be little bottles of that in the laboratory. And those are little round pellets, and so you're going to pour those right into the dichloromethane solution. And you want to continue adding those pellets. So you'll add the pellets, you'll kind of swirl this around. If the pellets get hydrated, they stick together, and so you'll see them start clumping together. So you want to continue adding these calcium chloride pellets until they no longer clump, until when you swirl this around, you see some of these pellets moving around independently, in other words. Once you've gotten to that point, then you're going to decant the dichloromethane off into another flask. That is, leaving these pellets behind. You pour this off. If you have a difficult time doing that, you can get a clean Pasteur pipette and just draw it out that way, but you want to leave the calcium chloride pellets behind. One thing that I should mention about the calcium chloride, it is anhydrous. It does pull moisture out of the air, so make sure that you seal up the bottle of calcium chloride pellets when it's not in use. So once you've poured these out, please make sure that the bottle is sealed so that the remaining calcium chloride does not get hydrated. If at any point you have to stop after you've removed the dichloromethane from the tea, once you've gotten to this point right here, if at any point you have to stop, it's a good idea to just seal this up with parafilm and keep it in your drawer, or I can keep it in a fume hood somewhere. That might be a better idea because we don't want these fumes going off into the lab. Often what will happen, because dichloromethane has such a high vapor pressure, it'll just go ahead and evaporate. And what you'll see here then is crystals inside this flask. Those crystals are caffeine. And so there's no problem with that. All you have to do, if you still have moisture left in here, is add more dichloromethane, then add your drying agent, and then decant off the dichloromethane. Or if the drying agent's already in there, just add dichloromethane and decant off into another flask. The next step is boiling off the dichloromethane gently in the fume hood at very low heat. If you use high heat, this is going to splatter out of here. You boil off the dichloromethane, and that leaves the caffeine behind. Before you do that, it's a really good idea to weigh the flask. Actually, weigh your final flask that you're going to decant this into first. So you have the mass of the empty flask. Decant this into that flask after you weigh it. Then boil off the dichloromethane. The difference between the mass of the empty flask and the mass with the caffeine crystals in it, of course, is the mass of the caffeine. You'll need that for the yield of your extraction. As always, let me know if you have any questions. Otherwise, I'll see you in lab.